I want to thank Professor Fly for previous lecture for setting the stage to what I will talk about today. And he really did a great job because I teach boundary layer meteorology, and that's entire course. So synthesizing something in 40 minutes, it's a very, very difficult thing. Now, if I would have to isolate one lecture that you should be familiar with, that's boundary layer meteorology. Okay, you all live in boundary layer meteorology. Your whole life is in the first kilometer in the atmosphere. Sometimes you fly, then you go above a boundary layer, but then you still have to land one way or another to the surface. But we also live at the surface, and from time to time we have these thunderstorms. And thunderstorms are the most powerful weather systems that we have on this planet, okay? And there are all kinds of thunderstorms. There are isolated thunderstorms, there are systems of thunderstorms, which I will talk about today, and there are also hurricanes. Unfortunately, I will not talk about hurricanes or typhoons in this lecture. That would require another lecture, so maybe in the next edition of this school. So what I will talk about today is first isolated thunderstorms, and there are three types of isolated thunderstorms: single cell thunderstorms, multicell thunderstorms, supercell thunderstorms, and then systems of thunderstorms known as mesoscale convective systems, and they come as squall lines, bow echoes, and something known as mesoscale convective complexes. If I have time, I will cover the last of them, but if not, it's not a big deal. They are not these complexes are not so important in wind engineering. Also, if you have any question, you are welcome to stop me in the middle of the lecture and just ask. Raise your hand and just ask question, okay? No problems. So first, I think what is important to discuss here is where is the word? What are mesoscales? What does it mean, mesoscale? In atmospheric sciences, we have different scales of motion. We have microscale motion, we have mesoscale motion, and we have synoptic scale motion. Microscales are those scales where the Coriolis force that Professor Fly talked about are not so important, okay? Coriolis force is a consequence of the rotation of our beautiful planet Earth. And at microscales, when you walk from here to there, Coriolis force is not of importance. Same for the air. Synoptic scales are the biggest planetary scales. That's where the Coriolis force is of the same order as all other forces. If you neglect Coriolis force, well, you're doing a huge mistake. And mesoscales sit between. Mesoscales are just at the border of Coriolis force being important. So we would say there are different classifications, but mesoscales are between approximately 2 kilometers to 2,000 kilometers, or let's say just 1,000 kilometers, okay? When you are at a few hundred kilometers in horizontal direction, not vertical, then Coriolis force is important. When you are below, Coriolis force is not so important. So in these systems of thunderstorms, Coriolis force plays a very, very important role. Whereas in isolated thunderstorms, Coriolis force is usually not so important, okay? So Coriolis force is this mystical force. You can complete all courses in wind engineering, never study Coriolis force, but it's always lurking somewhere in the background, waiting to trouble you. Now, here is atlas of clouds. And imagine how boring sky would be if there was no clouds. But there are all kinds of clouds, and we separate them in based on the layers where they appear: low-level clouds, mid-level clouds, high-level clouds. And then there is mother of all clouds, and that's thunderstorm. It's the vertical development, cloud of vertical development. The lower base of thunderstorm cloud is usually a few hundred meters. Top of the thunderstorm cloud is over 10 kilometers in the atmosphere. First, in mid-latitudes, first 10 kilometers of the atmosphere is known as troposphere. That's the part of the atmosphere where temperature generally decreases with height. Then you go into stratosphere. That's where temperature generally increases with height. Anybody knows why temperature increases with height in the stratosphere? Nobody? You should know, because that saves your life every day. It's the ozone. Ozone in the stratosphere at 25 kilometers or so absorbs ultraviolet radiation. We all live, and the stratosphere is warm. These clouds can reach stratosphere. That's how deep they are. Okay, so let's first start with isolated thunderstorms. Here is a photograph of isolated thunderstorm, and we also often, official name is cumulonimbus cloud. We often call them also anvil clouds, because indeed they look like an anvil, if you have a little bit of imagination. What are dimensions of these clouds? As I said, in vertical direction, 10 kilometers, in horizontal directions, dozens of kilometers, okay? And these isolated thunderstorm clouds come in three flavors: single cells, multicell, supercell. I'm not native English speaker, as you can see, and all my life I'm trying to figure out why single cell has dash and multicell and supercells don't have dash. So maybe Professor Fly can tell me later. But I never learned satisfactory reason why only single cell has a dash and these two don't. But you should remember that when you write papers. So they are different in terms of characteristics. Single cells usually occur when we have very low wind shear, and so importance of boundary layer meteorology. Shear means winds are pretty constant with height. It doesn't necessarily mean that winds are weak, although usually they are, but it means that wind speed is not changing with height profoundly. Weak change of wind direction with height, and isolated convection. So that thermal bubble that initiate clouds is very isolated. Multicell thunderstorms are, as you can see, same in terms of wind direction and convection, but they usually occur when we have rather strong wind shear. And lastly, the most powerful clouds that our planet can produce are the supercell thunderstorms, strong wind shear, strong wind direction shear, strong wind speed shear, and very strong convection. Okay? Any questions? So let's first start with single cell, then multicell, then supercell clouds, okay? So also, why this lecture in this course? Actually, many of you could probably finish your engineering education never knowing about thunderstorms, because we generally in wind engineering think about extreme winds. But these extreme winds are produced by thunderstorms. So why not knowing, why having thunderstorms as some black box that you just imagine is producing strong winds? You can understand the dynamics, and that's what I will try to convey in this lecture. So single cell thunderstorms have three stages of development, okay? And the first stage is called cumulus congestus, an early stage. Cumulus congestus are these clouds of vertical development that are still not thunderstorms. So cumulus, that word cumulus, means that cloud is thicker than wider. Okay? Clouds that are wider than thicker are known as stratiform clouds. So these are, these are small cumulus clouds. Official name is cumulus humilis, cumulus mediocris. So let's say this cloud over here continues growing. It will become something like that. This is still not thunderstorm, but it's on a very good direction to become thunderstorm. Okay? So generally, if this is diameter of the cloud, cumulus congestus clouds are approximately 1.5 times diameter in depth, okay? And what is the main, this is an important sentence, what is the main characteristic of early stage? The main characteristic of early stage of thunderstorm development, that entire cloud is updraft. There is no downdraft. Everything is just updraft. Cloud is growing, okay? That's how we identify the first stage of a cloud. And you can see here that I indicated, because this is single cell thunderstorm, that the wind shear is very weak. Winds are schematically here are not changing with height. I put some small changes so it doesn't look artificial, but that's the main characteristic of single cell cumulonimbus cloud, okay? One more time, in the early stage, the whole cloud is just an updraft. And you can see that the base of the cloud is usually at positive temperatures, and then the top of the cloud and middle of the cloud is at negative temperatures. And then we have mature stage. This is now already a stage that is of importance in wind engineering. In mature stage, you have occurrence of downdraft, okay? So if I would hide this part of the cloud and you only had updraft, that would be early stage. But this, I don't have time to talk about, but this updraft creates precipitation. And this precipitation, rain, hail, all kinds of particles start falling down, and as they melt and evaporate, from your thermodynamics courses, you know that evaporation takes energy. So this air in the downdraft is negatively buoyant, we would say. That's a fancy word. It's just colder than the surrounding air and it starts sinking. And this is what we call mature stage. Downdraft reach the surface. These lines represent rain. Any questions? So that's how the cloud in the mature stage looks like. Now, when this downdraft hits the surface, in principle, it can create high intensity winds. But in the case of single cell thunderstorms, that rarely happens, okay? That rarely happens, that this downdraft is so intense that the wind speed close to the surface will be high, but sometimes it can. And lastly, we have the third stage of cloud development, single cell thunderstorm, and that's called dissipation stage. Now, if you follow the logic, it's clear what dissipation stage represents. Early stage, whole cloud is updraft. Mature stage, cloud has updraft and downdraft. So clearly, dissipation stage means all cloud is just downdraft. The cloud is dying off. Why is it dying off? Because there is no more updraft. Updraft is what is supplying this cloud with moist air. Everything is just downdraft, and the last feature of this cloud that will survive sometimes for many hours afterwards is the anvil, the top of the cloud. So that would be a schematic representation of three stages of single cell thunderstorm in the atmosphere. Single cell thunderstorms are actually, they are the weakest, but they are sometimes the most difficult to forecast because they are so isolated. And numerical weather prediction models have grids that are few kilometers, 2-3 kilometers large. And therefore, it is very difficult for such coarse grids to pick up very isolated convection, very isolated clouds. The bigger the cloud, the easier to predict in terms of weather forecast. Okay, any questions? If not, let's see why this cloud, single cell thunderstorm, is the weakest of all thunderstorms. And it's the weakest of all thunderstorms because of this wind shear. You see what happens when we have this downdraft. When we have this downdraft that hits the surface and spreads radially, just like a downburst that I will talk about in the next lecture, this downdraft is cold and it spreads radially. And then just as I'm walking and I'm displacing air, this downdraft is displacing warm air. If the warm air is also moist, a new cloud will be formed. And now the key feature of single cell, because that wind shear is weak, spreading downdraft will spread too far from the parent cloud. So even if this guy forms, it will not be connected with the parent cloud. So perhaps you get new thunderstorm here, perhaps, but that thunderstorm will not be attached to this. And this cloud is dead. The moment you stop updraft, it's like a car without fuel. There is no more cloud. And why is this updraft stopped? Because updraft is over there, far away from the parent cloud, okay? And we will see in a few minutes that is not the case in multicell thunderstorms. So to summarize in one slide, single cell thunderstorms form when we have weak wind shear. They go through 3 stages. Stage number 1 is the early development stage, and this is even not thunderstorm yet. This is just strong cumulus cloud. Stage number 2, we have thunderstorm because we have updraft and downdraft. And stage number 3, we have dissipation, no more updraft, okay? Vertical velocities in the updraft in these types of clouds are not very strong, 5-10 meters per second maximum. You will see in supercells, updraft can be 60 meters per second. That's just something I cannot imagine in my head, because wind 60 meters per second would knock you down, but in the thunderstorm it goes vertically up. So in terms of severe weather, because that's what is important after all in this course, single cell thunderstorms sometimes have very intense rain, but generally they don't produce any severe weather, okay? But then we go to multicell thunderstorms. This is a photograph of a multicell thunderstorm. You can see again, there is this huge anvil that is not even in the, there is this huge anvil, there is this cloud, and there is yet new cell that is being produced. There is fresh cloud, so to speak, that is right next to this big old cloud. And you can see it is attached to the parent thunderstorm. And we will see how that happens. Here is another photograph of multicell thunderstorm. And if you are a little bit artistic, so to speak, you can see with your own eyes cells. You can see one cell, another cell, another cell, another cell, another cell. It's a series of cells merged together. Now, I said these types of storms happen in the environment when the wind speed shear is high. That means winds are changing substantially with the height, okay? And we will see why that matters. And you can see that matters greatly. Again, all these, when I teach mesoscale meteorology, that's just like boundary layer meteorology, entire course. So I'm skipping here many things, particularly equations and whatnot. But it can be demonstrated, but also you can just imagine. If this is the shear of wind, you can see the top of the cloud will be moved in that direction further than the bottom. So you can see that this downdraft that spreads is not spreading symmetrically, okay? Because the top of the cloud is advancing faster than this leading edge of the downdraft, and therefore these new clouds now form close to the parent thunderstorm, and they are attached. And the storm is just rolling forward, so to speak, okay? Again, we have downdraft, we have precipitation, and we have updraft. These 1, 2, 3, 4, 5 are different cells. In this schematic, cell number 5 is the oldest cell about to dissipate. These two, this is already dissipating cell, This is cell in mature stage. We have updraft and downdraft, and these two cells are in the formation stage. Okay. I put here a few things, but I'm burning time. So overshooting top. Overshooting top means that the top of the cloud is above troposphere. It went into stratosphere that I talked earlier. So that means top of the cloud is 15 kilometers above the surface. And these clouds at the inlet of the storm are known as shelf clouds. And they sometimes look very magnificent. And then also this rotating outflow can form sometimes a cloud known as roll cloud. So in terms of cloud motion is not an easy thing, because you see, when I walk from here to there, I am literally moving myself. But cloud is not rigid body. Air can blow through cloud. So for example, if you take a wooden stick and you throw it in the river, the stick will go together with the river, because the water cannot go through the stick. But imagine if the water could also go through the stick, so it would be much more difficult. So what I'm trying to say is that clouds move in two ways. First, they move just like people. They move, okay? And they move thanks to wind that is moving them. But another way the clouds move is that, imagine if I'm here, I disappear, and I teleport myself here. I disappear here, and I materialize here. You see, let's say this is top view of a cloud. These are cells, okay? 1 is the oldest cell, 2 is younger, 3 is even younger, and 4 is the youngest cell, okay? So you see, cloud moved from here to there. Cell number 1 will disappear, it's old cell, but cell number 5 will be formed here. So you can see that cloud also propagated in this south direction, despite it never moved in south direction. That's because new cells are being created here, and old cells are destroyed in the northern part of the cloud. So if we go in the next moment in time, now cell number 1 is maybe completely dead. Cell number 2 is about to die, but new cell number 6 emerges here. Okay? So we call motion, just like me walking, motion of the cloud, motion of the cells. And this way of cloud growing by new cells being formed on an edge of a cloud is known as cell propagation. So clouds move and propagate. Moving means just me walking, and propagation means, I don't know, new cells being generated at an edge of the cloud. So when you vectorially add these two, you would say that the whole system is moving like so. Is that clear? Any questions? Okay. So here is another photograph of a multicell cumulonimbus cloud. You can imagine, you can see different towers, different cells with your eyes. Severe weather, these are more severe because they're lasting longer than single cell thunderstorms. So they are more severe than them. But they are still not the most severe. Multicell thunderstorms are generally the most common type of thunderstorms in mid-latitudes, okay? They are more common than single cell. Yes, you can also check my YouTube channel if you want to see more information about clouds, wind engineering, wind energy, and non-Newtonian fluids, pressure, anyways, many things. Supercell thunderstorms. This is the king of all clouds. There is nothing our atmosphere produces that is more severe than a supercell. Now, fortunately, supercells are not so common, very rare. Maybe you get one per year. But when they happen, they can create extremely severe weather, tornadoes, strong downbursts, lightning, and so on. And these clouds can sometimes rotate. Entire cloud is rotating. This is sped up, so usually you don't see it literally with your eyes, but they do rotate. This is another supercell cloud. You can see they look like those muscular dogs. When you just see them, you see trouble coming. Now you might say, okay, this cloud also has some updraft that clearly spreads like that. This cloud does have updraft, but the situation is much more complicated. When I teach mesoscale meteorology, supercells are 3 lectures because they are so 3-dimensional. Well, it's not 3 lectures per dimension. It just happened to be about 3 lectures, okay? But I'll give my best to explain dynamics in a supercell. Here is idealized plane, and here is an idealized supercell thunderstorm. Storm is moving in this direction, and you see there is inflow that spreads, creating this anvil. These triangles in atmospheric sciences, they represent gust front. They represent the outer edge of that downdraft that hits the surface and spreads. We use blue triangles usually to indicate, and the teeth, the forward edge of the triangle indicates in which direction the flow is moving. But to understand these clouds, we really have to look at 3 dimensions. Here, again, Professor Fly talked about how wind changes with height. Very important what I'm about to say. These are winds relative to storm. These are storm relative winds. If you were riding on that storm, this is the wind profile perpendicular to storm motion, and that over there is wind profile in the direction along the storm motion. So you can see that wind profile is such that if this is 3-dimensional, you have to imagine a little bit. Imagine I look into this cloud from this direction, okay? What I would see is that projection of the cloud over there. And I see that projection of the cloud, and you can see that these winds are such that we will have inflow that spreads in this direction, okay? But now if I look at this cloud from here, okay, then I project it over there, you can also see that storm relative winds are such that you will have inflow at low elevations that spreads like so. Now the question is, why didn't I put 3-dimensional picture in previous clouds? The reason is, if you remember, I said supercells, these types of clouds, happen when wind direction is changing with height. And these profiles mean that wind direction is changing with height significantly. So there is no other way to represent it but 2 different or multiple planes, okay? Is this clear? Can you imagine what I'm describing here? Now, these regions over here we have usually the most intense hail precipitation. That would be the northern side of the cloud. That would be here. And we also have quite strong rain in the forward part of the cloud, and we have extremely strong rain in the back of the cloud, which would be here, okay? It's just 3-dimensional. You have to wrap your head a little bit around it, okay? So if we put everything in one picture, I'm not going to go now, but it's 3-dimensional picture like so sometimes, but the most important thing that I would like you to remember is that you see here I'm indicating that wind speed, the length of the arrows, is increasing with height, but wind direction is also changing, okay? These are the environment. And the consequence of the change of wind direction results, as you saw in previous slides, that the updraft and downdraft are decoupled. Updraft does not interact with the downdraft. The biggest threat to the updraft is the downdraft, okay? Because updraft wants to go down. Well, if downdraft clamps it down, it's not good. So if updraft is decoupled from downdraft, that's very good for cloud life. Here is the top view of, so this would be vertical cross-section. Horizontal cross-section, the updraft of these clouds is usually called mesocyclone. Again, meso, now you know what meso means. Order of magnitude about 2 kilometers or more. So this mesocyclone is several kilometers wide. But very importantly, supercells have two downdrafts. They have a rear flank downdraft and they have forward flank downdraft. Forward flank, both can create strong winds, but generally rear flank downdrafts are nasty. Forward flank downdrafts form just like any downdraft. Precipitation is melting, ice is melting, rain is evaporating, and so on. A rear flank downdraft is more complicated. In addition to these processes, I can show you here. You see, here, this is forward flank downdraft, just precipitation that is evaporating. But a rear flank downdraft also happens because of the interaction between mid-level winds and updraft, okay? There is no other way but describe this mathematically, which I'm not going to do it, but you can read more about the so-called vertical pressure perturbation gradient force. Well, or you can ask me later and I'll explain more. But the rear flank downdraft is more complicated than the forward flank downdraft. At least you can remember that partially it forms because of the interaction between outside winds and the updraft in the cloud. Any questions? So here on the right, you see idealized schematic of a supercell thunderstorm. Here yes, tornadoes that I'm going to talk about in next lecture usually form between updraft and downdraft. And you can see it also there. Tornado usually forms between this updraft known as mesocyclone and this rear flank downdraft, usually somewhere there. So here are two figures of supercells captured by meteorological radar. This is radar reflectivity, that is efficiency of particles in the atmosphere to reflect electromagnetic radiation. So red color means a lot of reflection, that means large particles in the cloud, precipitation, hail, whatnot. And the typical signature of supercells is what we call hook echo, as you can see here. And now you know after this lecture that this over here is rear flank downdraft. Here is updraft, and over here is forward flank downdraft. And you can see they're quite similar. This one produced one of the strongest tornadoes in the United States. And this one was also extremely, extremely severe supercell thunderstorm. Now, okay, let's just talk about it. I'll talk what I have to say if I go over. I love this so much, so I will probably go over time, but I'll stop. So I will rather not say everything I have to say, but I'll say in details what I want to say. There is a concept of vorticity in the atmosphere. You see the profile of wind that previous lecturer talked about. Again, without going into mathematics, you can imagine that this profile of wind will result in these vortex tubes like so. Wind speed here is higher than here, and you will have vortex tube developing like that. Now, there are two types. You will see why I'm talking about this. There are two types of vorticities. If you have, these are storm relative winds. This is not wind that anemometer would measure. This is wind that thunderstorm observes. If these vortex tubes are perpendicular to the storm relative winds, we call that crosswise vorticity. If the vortex tubes are aligned with storm relative winds, we call that streamwise vorticity. Okay? So here is one vortex tube, And here is another vortex tube that is affected by convection, hot air rising. And then, of course, mathematically it can be demonstrated, but with your own eyes, you can see that horizontal vorticity is being transformed into vertical vorticity. What do you think? Just say A and B. You saw a photograph of a cloud rotating. Do you think A is more likely to create rotating clouds or B? If you can imagine, cloud is being formed here and cloud is being formed there. Which one is more likely to rotate, A or B? I'm not going to ask you why, so you can just throw A or B, okay? B, that's correct, B, streamwise vorticity. Why? Why? I'm kidding. So anyways, you will see why now. Supercell formation from crosswise. Let's look into A, how supercells form when we have vorticity as in A. Here is horizontal plane, here is height, wind is changing with height, wind direction, wind speed. Here we have a vortex tube, like so, and this vortex tube, let's say there is some very hot surface over here, it's being deformed in a way that you get something like this, okay? So you have horizontal vorticity becoming vertical vorticity. And if there is enough moisture in the air, cloud will form. There is no moisture, nothing happens, okay? Now, again, you're all engineers. You know that in the center of the vortex, pressure is lower than outside. So in the center of the vortex, pressure is low, which means you have additional updrafts forming here. Now, you might say, if you create vortex here, it's not so low pressure. You're right. But you have to imagine these are extremely strong vortices. So strong that the pressure drop here can be much higher than this thermal instability. And over time, the cloud grows, and actually the updraft in these vortices is stronger than the updraft that is thermally driven. This only happens in supercells. But over here in the middle of the cloud, you will start having precipitation. And this precipitation starts falling down and it's split, and then it's even more complicated. You get different twisting now of the lines. But eventually this cloud splits in two. And you have something that is called right mover. So this was cloud at the beginning, cloud splitting, and two clouds after the split. And here you can see, I will finish in 1 minute, okay? Because I see I will go over time. Here you see one supercell splitting into two supercells, okay? In terms of severe weather, these clouds produce everything, okay? Very strong downbursts, very strong tornadoes, hail, lightning, everything, okay? Any questions? Everything is clear or nothing is clear? Yes. You can just ask. We don't. So the first question that the gentleman asked is, the clouds are moving, but they are moving much slower than wind speed that they produce, if I understand correctly. So do we need to study cloud motion? The answer is yes. Because cloud is, let's say this is one city, this is another city, so you have to study how the cloud will traverse from one city to another. But also, so you have to know where the cloud will go. Now, to give you more concrete answer, clouds usually move at the velocity that is average of the velocity along the depth of the cloud, okay? So that's one, I mean, not always, but if you don't have any other data, this is a good assumption to take. And no matter how slow that velocity, you should always add it to velocity of the outflow, okay? And it's simple because this is now also a matter of research. Translation velocity of the storm can just vectorially be added to the outflow velocity. It's like when you are in the car, you throw this microphone, initial velocity of the microphone is the velocity of the car. The same is this downdraft has initial velocity of the moving cloud. And your second question is, if I understand, you investigate downdrafts by impinging jets. Am I right? Or pipe? Yes, and then you study jet that is hitting the surface. Yes. So many people, I'll stop here. You can ask me about. I wanted to cover, by the way, supercells and multicell storms. These systems are not so important. I mean, they are important, but you can ask me later. But to answer this question, if you have a jet that is going from a pipe, then clearly that's not how cloud produces jets. So if you want to study origin of downdraft, then that experiment is not correct. But if you want to study how downdraft spreads once it hits the surface, then that's pretty good analogy. It's not perfect analogy, but it's pretty good analogy, particularly in the field of wind engineering, okay? So if you want to do research on how these clouds, dynamics of clouds, jets are not good. But just studying outflow, they're good. Any other question? Yes. Also, you wouldn't believe it, this screen is so hot. 70% of climate change in this city is consequence of this screen. Yes. Yeah, the wind speed change with height. So let's say the single cell thunderstorm, because as the storm is evolving, winds are evolving. So let's say single cell thunderstorm started with very low wind shear. Winds were weakly changing with height. But times are changing and wind speed started changing with height profoundly. Well, that means there is a good chance of single cell thunderstorm transforming into multi-cell thunderstorm because the wind profile in the atmosphere changed with time. That's the main factor that dictates whether you will, which type of thunderstorm you will have, is wind profile, yeah. And the first word, did we figure out what is the first word? Ah, dash. Okay, yeah. Ah, that was just a joke. That was not very good. So I said, I don't know why in English there is single dash cell and there is no multi-dash cell. It's just like, okay, I shouldn't make these jokes. It's just like, I don't know what's the reason, okay? But ask Professor Bly to answer that. I don't know. He is native English speaker. It's a mystery if, I don't know. Okay, well, that's end for this lecture, okay? Any other question? Yes. Well, students. Okay. So the answer is there is basically no clouds in the stratosphere, okay? Stratosphere is what we would say statically stable. And you can clearly see that because temperature is increasing with height. So you have warm air above cold air and the air is just happy to be like that. And that's why there is no, when the storm reaches stratosphere, it's dead end. It can penetrate a little bit because it has a lot of momentum, but it cannot develop, okay? So when I talked about storm moving, I didn't mean like they move vertically from troposphere to stratosphere. They just vertically develop in that direction, but they move horizontally, you know. So that's the first question. What was the second question? Did I answer? Ah, yes. Yeah. Thank you, Professor Kardoli. That's excellent question. You can see why he's professor. So the question is, so first of all, yes, for hurricanes, it's much simpler. That's because hurricanes are so large, and just as you said, they form over sea. And at the end of the day, when we do climate projections, we use climate models. Now, climate models have to run for hundreds of years or decades. So the grid has to be small. But even small grid, you capture ocean. Ocean is huge, 70% of this planet. So you have pretty good understanding, what you said, how temperature, sea surface temperature will change. But now when you go to climate simulation, these clouds are tens of kilometers and your grid is 100 kilometers. So they don't exist in climate simulation. There is no clouds in climate simulation. So you can only infer what would happen. And infer means you will always make some mistakes. Now the parameter, to answer concretely to your question, one of the parameters that people use a lot is known as CAPE, convective available potential energy. That is energy available for air to rise in the troposphere. And you can infer that from these sparse 100 kilometer apart cells, okay? But in the biggest difference, the biggest issue with climate simulations is that you don't have clouds. And this CAPE is affected by clouds. So and you are not resolving clouds properly. So the studies are conflicting. In some parts of the world, they claim they found positive trend of indices, namely environments prone to thunderstorms. So they would say that it seems to be that we will have more thunderstorms. Some research suggests we might have the same number of thunderstorms, just like for hurricanes, but they will be stronger. Because many researchers think we will not have more hurricanes. We'll maybe have the same number, but they might become stronger. But to conclude this long answer, the reliability of results for thunderstorms is much, much weaker than for hurricanes because of their small scale, and there is nothing we can simulate in these climate models. So it's just inferring. Any other question? I can stay here 2 days. It's fine. Yeah. Yes, it's time for coffee. Thank you.